is on mic and mic.
Okay, good afternoon, everyone. Welcome to the departmental seminar of this department. So today is a very special day, and so we have the pleasure of having our very own Professor Ranjit Biswas as the speaker today. He has kindly agreed to deliver the seminar today, and we hope to have a very invigorating discussion today. So, of course, Professor Biswas doesn't need any introduction, but I thought I'll just say a few words, particularly for the maybe the newcomers to this department. So, Professor Biswas is one of the very rare scientists who does experiment, theory, and computational work with breadth and depth of expertise. And he has developed a kind of contributed pioneeringly in the general field of studying complex liquids, studying the physical chemistry of complex fluids like eutectic solvents, ionic liquids. Has made pioneering contributions to this area, and that has been appreciated and recognized in the form of he has been elected as the fellow of the National Academy of Sciences last year, and the citation exactly reads that he has his contributions in experiment, computation, and theory of eutectic solvents and ionic liquids. So that's a great achievement, and congratulations from all of us. And also, I would and I would also like to highlight that not only his in terms of scientific achievements, but also 8 of his students are faculty in different institutes all across India, and so those are his achievements as a teacher or supervisor as well. So it's a pleasure for us. So with that, with a few brief words, I welcome Professor Biswas to deliver this seminar.
Thank you, Suman, for your kind words, and thanks also for being departmental chairman. You invited me to give the first talk, and I hope this continues. And many of my faculty colleagues, or all of my faculty colleagues, time to time, delivers seminar here, which help us not only in knowing what we have been doing in the department, but also kind of gives us an opportunity to interact and kind of enjoy each other's science. So the title is a little bit of provocative in the sense that bond that pays dividends and assigns identity, not gives you property. That's kind of something share market. I kind of borrowed words from there to encourage students to come. At least it should strike their imagination. And I'm essentially doing physical chemistry of small molecules. It's chemistry because I deal with molecules, and molecules have bonds. So as soon as bond forms, chemistry starts. So in that sense, chemistry is different from physics, and it is physical chemistry because I use the knowledge of physics. In physics terms, because I explain things in terms of interactions, and interactions is essentially a matter of physics. So that's how physical chemistry is physical chemistry. The small molecules, or assembly of small molecules, are essentially not only pure systems, but multi-component systems, starting from binary, ternary, and quaternary. I worked on a variety of complex systems, as already elaborated by on in his introductory remarks, but I'll take probably these 4 as representative examples and kind of stress the point that how the bond, hydrogen bond, or hydrogen bond structure actually gives or assigns that identity property, the physical-chemical properties by which a solvent is known, is essentially because of its ability to retain the hydrogen bond network structure. Once that is gone, it starts behaving like something different. Water may appear as a non-polar solvent, although we know it's highly polar with a dielectric constant of 8. Well, let's start with this. These are some pictures for people who would like to see exactly what I am talking. These things are essentially representing the hydrogen bonds. And this system is acetamide hydrogen bonds. This is essentially artist's view, not necessarily. It just limits by only making hydrogen bonds as I have seen. But in solution or in liquid phase, it may have three-dimensional structures with many permutations and combinations. However, these are only represented pictures, and this particular compound, at room temperature is solid, its melting temperature is 355, and static gravity constant of 65. So pretty high dielectric constant liquid in its molten phase. But when you add with some electrolyte, it just comes down the melting temperature of the mixture. It remains a stable liquid at 300 K, and that is termed as liquid solvent because this liquid is formed because of deep depression of freezing points. Not only the freezing point of acetamide itself, but these electrolytes, ionic compounds, are all high melting solids. So they are having something like 450 or 500 K as a melting temperature. So at least about 100 to 150 Kelvin is getting down when you mix them together at certain proportions and heat them, make them liquid, and then just pick out the heat source and allow them to cool down slowly, and you will see that the system is locked into a liquid phase, which is metastable. It is metastable because they actually at this temperature should be solid, but since the frustration of lattice, because the interspecies interactions is not allowing the molecules or the ions to get back to their designated lattice position, they cannot liquefy. So that's why they are metastable, and you see many of the features that we have seen also many of the features of metastable systems. For example, this supercooled glass, but that is not the focus, and I will not mention that. I am only showing you these are the kind of hydrogen bonds when you throw salt in molten acetamide, and what happens to its dielectric constant. That's the question. I'll show you. Let me keep it that as something for the time being not told. And this is kind of another system, beaten urea water. So this is the beaten molecule, and this is urea, and it can have various kinds of interactions. So this is binary interactions between butane and urea. When you have water, water will also compete with these interactions. It will try to interact with butane as well as urea as well. This is butane urea water hydrogen bond. You can see this that I have shown here to represent the picture how simultaneously these three species can get locked into some kind of hydrogen bond interactions. And this is urea water interaction it's showing, and this is another system, glucose water interaction, probably one of the most important interactions which has direct relevance to our body functioning. Is glucose water interaction. And then we have also studied disaccharide water interactions through trehalose water or sucrose water interactions. That's monstrous like diagram. Don't be afraid by seeing these pictures, but only it is representing that this kind of interactions can change the property of a system altogether. Water may not remain as water, urea may not remain as water in a mixture when you actually force them to interact either as a minority component, minor component, or in a mixture, some proportion. Well, this we look at longer. That was as early as sometime in 2021 or 22, and there we studied water, just focused on water in a mixture, glucose, water, urea. And this glucose, water, urea, the water is not a major component. That was kind of a semi-minor component. And what we are showing here, the water that is forming hydrogen bonds with various components. What is their kind of percentage? For example, here the water-water hydrogen bond, water-water direct hydrogen bond is something like 78%. While water urea and water glucose, these interactions are something like 26% and 50%. This doesn't mean that these water molecules are not participating in hydrogen bonding simultaneously with other species as well. And when we looked at that, this is telling you how much is that. Glucose, water, urea. Like one water is there, it is interacting with another water molecule. And this water, this end water is interacting with glucose, and this end with urea. So that is something like 9%, and this species looks like this. Similarly, if you have glucose, water, urea, water is mediating interaction between glucose and urea, and that is something like 7%. So why I'm telling this? These are simulation results. This tells you that if water interacts this way, then the next question would be that celebrated tetrahedral structure of water. What happens to that? And also that we know that on an average, water has average number of hydrogen bonds, something like around 4. Whether this water-water hydrogen bond is also gets reduced significantly or not. And if that is reduced through interactions, what exactly happens to those characteristic properties of water involved? For example, what happens to its direct constant? Well, this is the simulation results. What I'm plotting here, number of hydrogen bonds per water molecule. And this is probability of number of hydrogen bonds per water molecule. This is neat water exactly at the temperature at which this simulation was done, and that was 320. What we are seeing here, you see the peak is here where the hydrogen bond is nearly 4, number of hydrogen bond. But you see this peak is shifted appreciably, and it is going something like from 1 to 2. It tells that water-water hydrogen bond, that probability is now significantly reduced in this system. What happens to its tetrahedral angle? Water. We know that 104 degree, that is the kind of tetrahedral angle. It is not 109 degree 20 minutes because of the lone pair on the oxygen atom, lone pair free function. But it settles at 104 degree, and neat water gives you, of course, SPCE water, this is muddy water, and this peaks around 104 degree with some kind of population around 60 degree. But when it interacts in this kind of crowded system, what exactly happens? This is broadened, and you have a peak more at 40 degree. So population just gets transferred from this tetrahedral-like structure to more planar-like structure. And 40 degree, you see this kind of angle, water. So kind of planar water, not like a tetrahedral water that we see in this kind of angle.
I don't know this one. So one live question is that how is the measure?
It's not measure, simulation.
Well, another question.
I have a question that if angles are changing, that means energy might also be changing.
Of course, you can see it in your Raman. You will have seen it. There is a paper by Mark Marantelli. He did simulations as well as measurements, Raman measurements, where he measured extremely dilute solution of water in ionic liquids, and then he simulated, particularly the frequency where it should come. And definitely, we can understand that by using the single harmonic oscillator, K by mu. So your force constant changes as soon as its stress comes in. So the frequency will have shifted. Okay.
But when you say the Raman will give two kind of OH stretching.
Yeah.
One is the inter and another is the intra. And so intra is will remain as it is.
But the
other one, but that populations of this intra is much higher compared with the inter.
But then you are seeing at the where it is appearing, the energy. Energy, because your mu is root over K by mu. The mass, the reduced mass is the same. It is the first constant which is changing. So as soon as it is changing, your frequency will change.
Yeah. But what is the tentative percentage of this kind of configuration?
Well, I can't remember now. He has written a pretty big paper, But if you dilute an experiment, you cannot pick up only one molecule, right? He has done still the same experiments, but extremely dilute simulation experiments. Simulation one molecule he can take, one or two molecules, and he has done that. And he has found out that if you take something like 10 molecules, at least 20% of them just gets affected. Okay? But it is seen. You can see it in experiments. Okay. So. And people actually did this kind of measurements earlier also, like less concentrated solutions, but we did not think of explaining in that term. So not only that he has done his own experiments in ionic liquids, but also he has gathered, as one does, cumulative survey and told that how water band is now changing when they are looked at in propylene solution or propylene solutions or some kind of other alcohol or complex systems. Well, as soon as you see that water is losing its hydrogen bond so extensively and its tetrahedral structure is so significantly compromised, you understand that a kind of imagine that its dynamics would also be heavily affected. And when you did this, the simulation of the hydrogen bond lifetime, you see here the neat water at that temperature, the lifetime is about half second. But when you look at the water in this DES, it is kind of doubled. I don't know why, because you see this SHBT, the continuous hydrogen bond lifetime, this should not depend on viscosity. This system has a viscosity of something like 251 centipoise. Water has a viscosity of 1 centipoise. So it is 250 times slower in terms of viscosity. Its lifetime is slowed down by a factor of 2, the continuous hydrogen bond lifetime. So it is kind of sensing the environment, not the viscosity. Okay, but the other hydrogen bond, that is continuous structural hydrogen bond, over the entire simulation period, that is something showing you a slowing down of something like 35 times. In bulk water it is 4.5, whereas in this system it is 144. So just 35 times. Although, but this one actually is sensitive to viscosity because it is not the only one hydrogen bond with another molecule. It can break and then the molecule can move away, another molecule can come and again it form. So this actually monitoring accounts for hydrogen bond breaking and reformation. So this has the diffusion component, and as soon as you have diffusion component, it will have the viscosity information. But still, it is only 35 times. The viscosity difference is 250 times. So there is a kind of viscosity out there. So it tells you that the center of mass diffusion is not following the formal Brownian motion. It is not stochastic Brownian motion. Maybe water is jumping around, something like that. Okay. And exactly that is what it is when you plot MSD. Just see how slow it is. Just concentrate here, it is about 100 picosecond. And this 100 picosecond, the displacement of neat water is something like 1 nanometer square. That means if you square root of it, MSD on average, it is 10 angstrom. So 10 angstrom is 4 times of its water molecular diameter. But comparable time, in this DES, water is moving only about 1 angstrom. It is extremely slowed down. And that's what you are seeing here when you actually see it in an elongated time scale. To run a bigger time, something like 8,000 picoseconds or 10,000 picoseconds, and just plot. And you see here that this particular quantity, it should be 1 when it just attains the diffusive limit. In normal water, it attains the diffusive limit within 50 picoseconds. So at the 328. But here, this guy is not even going to. So the entire region, even up to 10 nanoseconds, it remains somewhat less than diffusive, subdiffusive kind of thing. Okay, it is so much slowed down. Naturally, if the water molecules are so slowed down, its dynamics are slowed down by the environment because of the interactions, the water molecules moving here may not be completely uh, blind to what is happening to the other water molecule happening over here in another space. And statistical mechanics allows you or provides you an avenue to look at that how long water molecules moving here and water molecules moving here are temporarily connected. That means how long they remain connected, how long me and my friend just goes together. And also statistical mechanics allows you to look at up to what distance this relation remains in. Long back in my group, who is in the audience, Tomisra did it for ionic liquid water mixture. So that time we wrote this paper, and this is from physics literature. And this chi4, the 4-point correlations, was actually done by Chongman Das. He was the originator of this. And then the glass people in the United States, they used this idea so much, people forgot about the neurophysics later paper by M. Phony and Chongman Das. And we read that paper and we thought that we would write it down, Bangla Kore. We just wrote it for chemistry. And people loved the kind of way that we wrote and explained what is this 4-point correlations. This is just shown here that the red particle over here, just imagine that is at the point R1 and this particle at R2, and I want to know that the dynamics of the R1 particle in this ensemble, it could be anyone else, any blue or red. I just for understanding, I just put in different color. How this particle, this movement of this particle is correlated, connected to the movement of this particle at a different place over a period of time. And when we calculate that, and this is kind of statistical mechanical expression, is telling you the density at position 0 at the beginning time, T0, and this is density at that same position and after a time T. This, how it is kind of connected to another particle position at R at that original time, and then the same particle, same position after that. So when you do that,
when you are saying this density, that
this
is
is number density.
number
Or
density.
single particle.
Yeah, that is there must be one number of particles rather than a single particle, right? But here you are talking about you are actually considering one particle, movement of one particle.
Now, here this is just for understanding. When you do it in simulations, you put your point, every particle you go on and you average it. Okay, so in terms of it, it's a density kind of term that you use it. Okay, so what you see here for neat water, this time is about 1 picoseconds. And believe me, when people read solution dynamics, is this the slowest summation component is about 1 picosecond. And this is something 10% or 9%. People did not find any slower component. Okay, but when you did the same analysis to water molecules of these liquid packets, which is 2 to 3 times slower in viscosity compared to viscosity, that you get a slow time about. When you did these measurements of the system, you got time scales in this component. So the water molecules, now people know where from all these slow times are coming. Okay, so
That was a function of both K and T, right? So the spacing also. But so
this is K equals to 0.
K equals to 0.
Correct. So because when you compare with measurements. So well, these are all simulations. Right? So let's discuss now some experiments platform I can get the same evidence or similar evidence telling that water is losing its hydrodynamic structure and behaving in a way which we are not accustomed to. Well, as in my access, I have dielectric glassation. So I did some dielectric glassation, for for a variety of systems. For students who doesn't know what direct induction spectroscopy measures, what it does, it just sends a frequency dependent electron and just measures the response in the system. And this response is nothing but there is a fluctuation in its spectrum. When you send the radiation, there should be a kind of light matter interaction, and matter itself will not interact. Density will not interact. In this case, it is the polarization density which interacts with the frequency dependent electric field, and it is assumed that the electric field that you apply is getting coupled to the fluctuation of the system, but then it is not influencing its natural way of responding. This is called linear response. I can give an example, kind of thing that say, imagine that you are walking and a slope. If the slope is kind of very steep, then you have to really careful on your steps. But if the slope is very friendly, very smooth, then you can just walk like you are walking. Okay, so under the linear response regime, what you measure is a measure of the inherent dynamics of the system. And you see here in the low frequency, it is the orientation polarization or the rotation of the molecule which responds first. In the low frequency, it is slow. But as you increase the frequency, then the first dynamics comes in. This is the atomic polarization where you have movements. For example, if you have OH oscillations, that actually creates a polarization field and that responds at the high frequency. And then still at the high frequency, you have the electronic polarizations, which is happening in the system itself because of the polarizability. Now, we have measured a system which is beaten urea water. And this measurement on a wide frequency coverage, hertz to gigahertz. And what you see here, very nice data. You see, 3 setups were used to collect data, but then they are merged so nicely. Okay, and then this is temperature dependence, and as you know that with temperature the viscosity is changing, so the peak which connected to the orientational diffusion should be occurring at the higher and higher frequency. Higher frequency means lesser time, and that's what is happening. This is 303K, which is occurring here lower frequency, and it is the highest temperature, which is occurring at the highest frequency within this temperature range. And this is some kind of analysis that is a multimodal. That means the relaxation is not single divide, it is a multi-divide process. Multiple relaxation steps are associated with the total relaxation, and this is kind of telling you how much percentage of each of the relaxation steps is contributed. But these relaxation steps for 1, 2, 3, or 4, you cannot actually ascribe to any of the components, individual components, because when you calculate the rotational diffusion constant or rotational time from hydrodynamics, namely Stokes-Einstein divide, you get relaxation time scales either too long or too fast compared to what you are getting from your analysis, these time constants, tau 1, tau 2. So that means it is not the hydrodynamic molecular rotations that could be assigned for taking care of these relaxation components. And you know these systems are strongly interacting in terms of hydrogen. So it is kind of foolish to assume that a molecule would be allowed to rotate freely. It would be definitely interacting, and would be its rotational motion would be highly quenched or hindered. So then you have to go to simulations. If there is a way to calculate or simulate the entire experimental spectrum, dielectric spectrum, in terms of piecewise interactions, then you can add them together, construct the full spectrum, compare with experiments, and see how good you are or how bad you are. And that also gives you an avenue to find out which part is contributing and how much. That was the end, and the next data is very nice.
What was the motivation to fix this composition?
say one more thing.
Where you get the liquid phase? Because as I said, this is liquid technique systems. So there is a particular composition where it gives you liquid phase, and that is accessible to your measurements. There are many compositions you can get liquid phase maybe around 500 Kelvin. We are trying to find out systems which are giving you liquid phase near room temperature. So that helps us. So we were surprised to get this kind of comparison. You see, it's beautiful. Experiment and simulations matching so well at 313 to 343, 30-degree difference. It's pure math. If you ask me to reproduce this for any other systems in simulations, I cannot do that. Join the whole video is smiling, and I told him that don't kind of be very proud that we have got it, because it's just pure luck. The interactions and see, these potentials are classical. And deep euclidic formation, this actually derives huge contributions from polarizability interactions. And in the classical simulations, where we are representing each system by model potentials, like just through some parameters, diameters, interaction, this and that, and such distribution, that's the domain of quantum chemistry. We cannot do that because that will demand huge amount of computation time and also very less number of particles. Okay, so this is with the caveat that I said that this kind of comparison will cause kind of some luck and some cancellations in the right direction, but still it gives you confidence. Then probably this gives you opportunity to look at what are different pieces that contributes to your response. And the statistical mechanics gives you that. When you do all those things, you arrive at. But before that, let me tell you, connect the experiment to simulations. This is your experimental quantity, frequency-dependent dielectric function system. And this connects to a quantity which is called phi t, and this phi t is nothing but normalized collective total moment potential. So what I showed you here is an example of macro-micro relation. Macro means you can get it via experiments, and micro means when that particular quantity that you measure in experiments can be related to microscopic quantities. And this is microscopic quantities. You cannot measure these fluctuations in experiments directly. It has to come via function. So, and what is M? M is the total dipole moment of the systems, and first order approximation, I can take it as a sum over the molecular dipole mu I. Well, then in my multi-component systems, I make another approximation. Statistical mechanics doing is very beautiful and kind of gives you a lot of easy window to make mistakes, control mistakes. Of course, you know what are you doing, and then their total moment I just write down as the algebraic sum of the total moment of each of the components. And then when I form correlations, I get that these correlations is essentially reducing down to three self-term contributions, that betaine, urea, water, and gas. Betaine, urea, water. And if I now can compute differently and separately, I can tell that how much is contributing to this. That's what we have done it. And this is when you convert it into E omega through some algebraic manipulation. Well, this is the simulation data, and you can see here this is total, and this is a kind of colored coded presentation. And you see here betaine is kind of contributing 65%, whereas water is contributing only 1%. Look at here, that constant something like 125. And how much is water there? Water, we know bulk water is something like 80, but SPCE water bulk has a direct constant is about 7. So how much water is contributing? It's probably 1 or 2. And this thing, this saga, is actually same thing at 313 or 343. And this is essentially the absorption part. And you see here the peak contributions, we have multiple relaxations. Well,
so this percentage of the specific interaction. So if I remember, you told that there are small.
Right. That just here I showed, right? You have this.
So sir, this 65%, 45%. So this is just the interactions happen in a small specific area. So like
From my whole system,
your
my
whole
simulated system, whatever I pick.
the simulation.
Because I have prepared the DQ technique just following the experimental composition. So I can take the number of molecules. That. Okay. And when I did the decomposition, what I found, you look at here, this is static dielectric constant. And it is giving you the contributions from each interaction component and 5 or 6 different temperatures. Notice here, this is line 1, and water at every temperature, it is showing its static dielectric constant is something like 1. It has reduced so much. It is within my simulation system, but in experiments also, the similar kind of reaction must have happened. That is the point. Okay, and also you look at urea. Urea we measured liquid urea, which melts at something like 405 Kelvin. The molten urea has a dielectric constant of about 70, and it has reduced to something like 10 below 10. That is because of extensive interaction with the RCs, hydrogen bond interaction. So these bonds, hydrogen bonds, as they lose, they also lose their identity. Urea is not remaining urea there. Here, I just want to highlight to show you, I will be very excited. You see the time scale? About 2 nanoseconds, the water has a dielectric constant, a dielectric relaxation time. The measured one is something like 10 picoseconds, exactly 8.6 picoseconds. But if you take it 10 picoseconds, and this is 2 nanoseconds, so something like 200 times slowed down. And also the analysis shows the dielectric constant is something like 1.1. Nevertheless, so you see the characteristic bulk water is there. Although this percentage is very low, there are some water molecules which are having 2 or 3 hydrogen bonds, yet still they are contributing. But there are major amount of water molecules which are kind of all hydrogen bond ruptured, interacted, slowed down, and giving a long component. Well, these are the viscosities. The systems are really viscous. At low temperature is something like 500 centipoise to here something like 100 centipoise. So we are actually kind of reproduce the experimental viscosity when we set the potential parameters, and this gives us kind of confidence that the relaxation that we are predicting is probably semi-quantitatively predicting what the experiment is doing. And our assignment of the relaxation channels is probably a kind of that. Well, and when you saw that water is slowed down by 200 times, so that means the water reorientational dynamics in this confined or the kind of this space, crowded space, must be extremely slowed down. So we individually looked at the reorientation of the water dipole. This is the kind of point dipole vector, and we are just following the correlation between 2 times. And this C1 is the degenerate polynomial first rank, and you see here water. Look at the time scale over here, so much slowed down. Okay, with log scale. So this tells us that water not only loses hydrogen bond, not only loses its characteristic structure, but also develops extremely slowed down dynamical. Well, that was the slow temperature. What happens to azeotrope? Azeotrope, you know, the most celebrated azeotrope is ethanol water. And if you have a mixture at room temperature and normal pressure, you start boiling, you can actually concentrate ethanol, water will go away, but not when it reaches 4.5. It will then start moving hand in hand together. The diffusion, consistent diffusion is together. They will leave the surface, the boiling liquid surface, but they will leave together. That means the liquid composition should equal to the surface combination. You cannot purify further once it is proven. Okay, and in that case, look at the hydrogen bond, number of hydrogen bond as you change the water process. This water, you see, it can hit even some kind of a very low value, 0.1, 0.2. That tells you that there are a lot of free water molecules. I mean, whatever hydrogen bond is not there. Ethanol is kind of uh, engaging them. And this is, you see here, this is 4.5%. Let's say azotrope at 351, what is happening to the number of hydrogen bonds, kind of thing. Huh? So, this one. So, the dominating water molecules are with very less number of water hydrogen bonds. And its structure is also kind of, you see how much it is deviated. This is your normal stuff, the red one, and this pink one is where it is. I mean, all the population is getting transferred to the blue one. It's telling you that the water molecules are there mostly kind of non-tetrahedral, linear kind of thing. This is the dielectric relaxation data. What I have plotted here, dielectric constant, use the same decomposition and looked at what is the component contributions. And here, our simulation is not matching with the experiment, as I said, not always. And what you expect all the time, that the qualitative trend you will be able to see, not the quantitative. Simulation never tries to look at quantitative. If it happens, it's just good. So this is your experimental data, and this is the simulation full. When I just kind of cut in and see what are the contributions, I have water, I have ethanol water, I have ethanol. What you see here, look at the low, notice the water ethanol at low concentration. This is your ethanol low concentration. Ethanol has a dielectric constant of about 30, but it is going down to something like 2, 3, or even 1. The same thing happens for water. When you go down to low concentration, you see here, it is just like same thing, because water has lost all its hydrogen bond. But still, these are all kind of speculations. Can we connect directly that number of hydrogen bonds and static dielectric constant, and just see or show that as the number of hydrogen bonds going down, your static dielectric constant is also going down? And you connect your experiment with simulations, because hydrogen bond, number of hydrogen bonds you can access via simulations only, and static dielectric constant you can both access via simulation. Well, that's what I told. And this is a system that we have been working very long time. I'll show you that we wrote first paper on this in 2010, when people probably did not realize that these kind of systems, systems, would have very exciting and interesting physical history. Well, so what we found out there, the thing is this, that this is molten acetamide. This is our data, which has a dielectric constant of 65. And as soon as we mix with these salts and molten phase we measured, we get dielectric constant about something 20 to 25. There's a huge decrease, and this decrease is actually continuing no matter what kind of identity of the electrolyte that we are using. It is just giving me dielectric decrement. Now the question is, from where this dielectric is occurring? But before that, you try to kind of characterize these systems. If it is glassy or fragile, what is the glaciation temperature, and all those things. And you see here, this is what I'm plotting, is glaciation temperature as a function of the potassium ion concentration for a system, acetamide plus. This is a very kind of typical system where you can change the alkali metal ion concentration, keeping the anion intact. And what you see here, these are our data. Too bad that our DAC system is not working. Very nice data, very nice. It's published. And you see here that this temperature is changing from 200 to something like 220 as I increase the sodium ion concentration. This is potassium going down. So sodium plus, if I increase it in my system, the glaciation temperature is increasing. And that means this, the cooperativity, the dynamic fragility of the system is increasing because of this relation. This is a kind of relation we have found, although it doesn't have any theoretical background from where it is appearing, but we would have found out. The fitting gives this kind of thing. And this tells me that sodium plus DES is more fragile than potassium rich system. And more fragile means the dynamic cooperativity is different, because fragility is directly proportional to the extent of dynamic cooperativity. Well, if I try to see where my systems belong in the classical fragility picture, this is the famous Angel's plot. You see here this SiO2, the least fragile system. The OTP is the most fragile system. In between is glycerol, and these ionic liquids and the many of them we worked on, and these are many of our data. And you see this falls between these two. So it's between glycerol and OTP fragility. Okay, and these are the kind of system that we have looked at, and these are ionic systems. And when you have ionic systems, you will have the ion-ion transitional part, because that doesn't have a rotation part, and you have to be very careful to get rid of that part. And if you don't get rid of that part, you will get in your low frequency stuff a big peak to divergence, because in your expression you have 1/1 divergence. So typically these are the things that we simulated, and what we got is essentially. But before that, since acetamide is host, I need to fix the potential for acetamide and look at how much dielectric constant I'm getting for acetamide. And this is the molten acetamide stuff, which I'm getting 65, very near to experiment. And also you need to look at the system size dependence and kind of dependence on what kind of model potentials you're using. So we found out the one kind of model potential is giving me very nice data. So we pick that, and then that model now allowed to interact with the various kinds of salts. And what we found out that 65 is now getting down to 30. Simulation now tells that interaction of electrolyte is reducing the static gravity constant of the acetamide in the. Earlier, people have found out kind of 10^7 mega value of that. So we proved that was wrong. But the question is that why is happening? So we calculated number of hydrogen bonds, and what we found out, neat acetamide is number of hydrogen bonds somewhere here in peak 3.2. And as soon as we mixed it with bromide or nitrate or perchlorate, we found out that it's reduced. Not only reduced, it is actually recognized the identity of the anions that I have used in my salt. The lithium perchlorate and lithium nitrate does the most damage compared to bromide. And then, if it is damaging is done at the microscopic level, what is happening in the molecular dipoles? Its orientational correlations with its neighbors. So these correlations, the orientational correlations, the dipolar orientation correlations, how it is maintaining relationship with the other acetamide molecules, that is embodied in this GK. And what you see here, this is for neat acetamide. You see here some value something like 2.2 or something like that, a long time value. But with time, it is changing because this more is coming interacting with the ions, and it's settling down to equilibrium value. And you see here, these systems are really. So it tells me that it is losing molecular correlations, and it might have some relationship with the extent of hydrogen bond it has lost because of the interaction with the anion. This is what I am looking for. Proof: the system is this, and this is average number of acetamide hydrogen bonds, and this is the experimental dielectric constant. And you see such a nice dependence. As the hydrogen bond is decreasing, the static dielectric constant also.
If for the potassium to sodium transitions, the counter ions also remaining same.
Same, that's right.
Oh, okay. Yeah.
That's right. Otherwise, the good stuff does
otherwise,
not.
yeah. So as you said that,
right. In that case, we change the anions.
Exactly.
In this case, we are changing the
Otherwise,
anions.
not makes sense.
So the same thing is also the superpolar. So this tells you that the dielectric constant, which is a response function, because it measures the fluctuation of the collective record. Anything that measures or connected to the fluctuation is a response function, right? For example, your heat capacity, that was connected to fluctuation of the number density, right? There, you can connect. age and then to number. Okay. So this is telling you that the local correlations are getting disturbed because of the interactions, and this disturbance is mediated by the loss of value. Well, conclusion, age-bound network does provide this solving. And as I said, that is deeply tactics are pretty close to our heart because it give us our identity. That when you watch myself and from me on this side is, and these are some representative publications over the years. And this is the paper 2010. If you do a literature search on DPU tactics, physical chemistry, you won't see any paper other than us around 2010. Once this paper was published, and then this paper in Journal of Chemical Physics, suddenly I saw exponential increase. Now, every journal does that. Why people did not do, I had an explanation. In 2003, these modern day diffusive solvents were invented. In the sense that diffutives are known, classical physical chemistry, you know, but that was actually in metallurgy, and they are high temperature stuff. Abbott in England, he first kind of synthesized pairs, donors and accidents, hydrogen bomb, the organic compounds, and he mixed them together and found out that at certain proportions they give you liquids near in 2003. But people, it did not catch the attention of physical chemists because that time ionic liquid was in its kind of, it was Shaburo pure all. Everybody was using ionic liquids for everything. Suddenly, after 2010, we showed that the physical chemistry itself, because these are just molecular systems, small molecules, but it gives you, my idea was to bring the glass language in these systems where we are working 100 to 150 K above the glass transition temperature. You just saw the glass transition temperature of these systems, thermodynamic glass transition temperature, is something like 200 to 220 Kelvin. Our experimental temperature starts from 300 Kelvin. So 300 to 350. So we are good 100 to 150 above the glass transition temperature. Yet we found out through our rudimentary experimental setup here at the center, telltale signature of deeply supercooled glassy system. That attracted the attention of our people. And they started. With this, I conclude. Thank you very much.
Fascinating and insightful lecture, fundamentals of physical chemistry. Sure, it was good for students. So I would expect some questions from the students. We had a lot of discussions. First, the students. Anybody?
They are sleeping. Too much.
Okay, maybe from the faculty.
They're just thinking too much. Okay. Question on the last part. You were showing potassium and smaller question.
This one?
Yeah, here. Is there any room of the size of the cation?
Well,
Because I mean, my understanding is smaller the cation, then you have packed structure around that.
maybe I have the answer. You see here, it looks like no lithium perchlorate. You see, perchlorate and nitrate. Are their size comparable? I don't know. Looks like perchlorate should be much bigger, but the impact on the number of hydrogen bonds, as well as the hydrogen bond, is the same. So I would say the impact should depend on ionization potential, charge by radius, or charge square by radius. So the smaller the ion, the more intense would be the impact. Because it will then immediately go and sit on either carbonyl oxygen or the hydrogen, amide hydrogen, or alcohol hydrogen, or whatever.
If nobody is having the
Raising hand. So please go ahead.
So, what the deep utilities system that you said, that is very interesting. So, whenever you said that this is the planar structure, can I
Water.
Yeah,
Water. Kind of. Some water only. It's not all.
So the planar structure. So that means that the interactions of the water thing is much more stronger, and there is no extension of the tetrahedral.
Tetrahedrality is more or less for some water molecules gone.
It's gone.
It's gone.
So they are only residing in the in some planes, like a one,
Like that,
something
all the
like that.
hands are like that, and
Like
it is
a-
tied to other systems.
Like exfoliations kind of stuff. Like you just go for like a graphene, you are exploiting one and two. Something
I
like
don't
that.
know that. How
Because
are they
no, why I'm
visualized?
asking, because in that case, Ranjita, you are supposed to get the viscosity to be anisotropic. Like then the measurement that you showed the viscosity and viscosity to be 200
There
centipoise.
is macroscopic viscosity or local viscosity.
The local viscosity,
Local viscosity.
not like a that
Not that
rolling
rolling
ball
ball.
or something.
Microscopic friction is definitely different because this system shows very strong dynamic activity. So, see, local viscosity is very difficult to define in statistical mechanics. There is no definition. So, what we can say, we can of course define friction. So, if I transfer this language to friction, then I can say that microscopic friction is very, very different. The molecule at one space is experiencing friction very different from the same molecule distributed to the other place of the solution. The microscopic friction is very, very different. That we have done to those single molecule or to solution or that.
So in the same way, like a dielectric relaxation will also be anisotropic. Like if we
If
just
you
do
plot,
that way,
if you plot, best way in experiment to see this, just do temperature in a direct relaxation measurement and plot the direct relaxation time, average time, or the storage time as a function of temperature reduced viscosity, and see how it is. And you will see that it is deviating from the hydrodynamic prediction.
so the hydrodynamic prediction that he was there because
I did not show it. You have done all the
so
same.
2 nanosecond is very much
Right.
like 100 or 200.
Right.
Yeah.
So it's telling you. And also this told you typho, the 4-point correlation. Yeah.
Can I just ask a quick question?
Yeah.
Very interesting correlation between dielectric constant and the average number of hydrogen bonds. But I'm just curious that the dynamics should be another parameter. Like I'm thinking that a single water can be freely rotating or it can be rigid, let's say. So now, if I have some kind of a trapped water which is not somehow trapped but not hydrogen bond,
Right.
so whether that water should have lower dielectric constant because it's rigid compared to a freely rotating. So even at the same number of hydrogen bond, if I now vary the dynamics somehow, do we expect that the dielectric constant should
rigid. When you said rigid, you talked about dynamically
trapped,
rigid.
dynamical rigid?
And now,
With
as
same
soon
number of
as
average
you
hydrogen
say dynamically rigid to an experiment, you make a comparison, innocent comparison. The comparison means the measurement that you are doing, it has a time scale. And that rigid, molecular dynamics itself, inherent, that is a time scale. So, now, if I want to say my dielectric relaxation cannot see those molecules, the molecular rotations are so slow, I have a frequency range up to 200, let's say, megahertz to 50 gigahertz. I cannot see them, but they may be slowing even slowly in nanosecond or 10 nanosecond domain, which I cannot capture. So then in that case, I have to have measurements which is going into sub-hertz. If I have that facility, and if I do that, then probably I can catch the dynamics on those.
intuitively expect that more rigid means lower dielectric constant. It's more like a state because it's not relaxing.
No, because dielectric constant here can go down on two ways. One is the kinetic, that is your dynamics, and the static. Static is that you are breaking its hands, hydrogen bonds. So the effective dipole moment is now getting reduced. And dynamically frozen means that those molecules are so tightly bound either to ion or among themselves, that during the experimental time scale, they are just outside the universe.
Yes, not let's thank